All right, good afternoon to all of you. So in the extended discussions that we are right now in the area of military avionics systems, we had seen the broad classification of the avionics in terms of abilities to offer services in domains such as navigation, communications, the use of varieties of sensors dedicated to the mission. Okay, so we are not talking of the mainstream aircraft flyability related sensor parameters, which are a whole different sort of assorted sensors. These are specific to the mission, okay, wherein you would be carrying dedicated sensors of certain kind, depending on the mission attributes. Then you also have the processing abilities, which are by and large identified as part of the management scheme, and the eventual requirement to project all of the information via an interface to the human element. So these are the two that we will be looking at immediately before proceeding with the typical integration solutions that exist. Okay, right. So the mission systems. So that's the next broad definition of military avionics. As you can expect, depending on the various types of sensors carried on board, either for the purpose of retaining the aircraft in an operational state where it can confidently execute a mission, or with the possibilities that the aircraft can deploy weapon systems, okay, which means it would have to carry some of these weapon systems. There has to be a very good understanding of the capabilities of the weapon system and the evolving nature of the war scenario that is developing in an theater of warfare happening in three-dimensional space. And depending on that, the precise type of weapon system needs to be carried and deployed, okay, at the specific phase of operation of the airplane. So this is a high level of information processing, and it is very intense in terms of the processing levels of the data that is streamed to the operator of the aircraft, okay, so who may be located on the ground or in a more conventional sense on board the aircraft itself, okay. So you have mission computers as the first element that is identified here, okay. Primarily, this can be understood in the form of the complex flight missions, fundamentally restricted in terms of their abilities to perform on account of the various limitations that are imposed by the airborne platforms themselves. The first and foremost of them being the SWaP-C, okay, size, weight, power, and cost. So restrictions imposed by them within limitations of which the overall flight mission has to be carried out, which as it is a very complex mission involving, if it is, for example, a multi-role aircraft, significant phases and operational abilities in the aircraft itself, okay. So clearly, the high processing demands that are being set on the computing platform on account of the significantly large data throughput requires a suitable avionics architecture defined computing ability. All right, so this is in turn identified in the mainstream processors, which are suitably adapted for aerospace applications. So in a manner where you now have high data integrity, which means that possibilities for potential corruption in the data during the operational phase on the data by the various algorithms, the processing stages involved, the porting of data across the various modules in the computing environment, the aspect associated with the multi-core or vertically stacked nature of the processor scheme, various scalable options available in the input and output aspects, and the graphics side of it, which is involved in visualization, okay. There should be a very concerted outcome that is realized out of the functionality in each of these domains of the computing resource that is available for processing the information. So the digital signal processing modules are very critical to the functionality of this mission computers. And one of the important players in this domain is the Collins Aerospace, who offers significant mission computation. Likewise, you also have general dynamics, which is able to provide significant abilities for the pilot as well as the choice of the air platform that is used in the battlefield, which in turn can provide advanced levels of situational awareness and combat system control. Okay, that will ensure complete success for the mission. Some of the attributes of this include processing for the actual nature of mission into which the aircraft is being deployed, the various sensor systems which are carried on board and related data processing involving them, display solutions, how does one reconfigure them to the very expectations that the pilots would have in terms of the multiple types of display options available, which may be either only projecting the information or may be a bidirectional scheme wherein you have an interface such as a tactile sensory display or a touch screen display through which controls can also be generated, okay, based on the information that is being displayed. You have also weapons and stores management, which critically informs about important aspects that support life as well as the aircraft functionality in the form of fuel, onboard quality of the air that is of a breathable nature, potentially even food supplies, and including options such as the power that is generated and the entirely dedicated area of stores management called as the weapons management. You also have in recent times what is called as information management. Okay, so how much of a curated information needs to be provided to the pilot in a manner where it would not end up becoming extremely cluttered and confusing so that the decision making ability of the human being is compromised. Such possibilities need to be severely vetted before the information reaches the pilot, who can in turn make a very confident judgment in a given warfare scenario. Okay, so all of these attributes go into that first element called the mission computing. You have evidently various types of sensors that operate at different frequencies in terms of the data throughput rate. Okay, so how much of samples per unit time or per second is being sent across, and that depends on the sensors. Some of them are very infrequent in the data that are generated by them. Others need to provide extremely high rates of data. So clearly all of this data needs to be processed and a unified representation of the information needs to be extracted from this data. Okay, so we are not talking of analysis of data. That is left as an activity potentially for a machine learning or deep learning algorithm to pursue. So the outcomes of that in terms of the interpretation is alone supposed to reach the human being. Okay, so that is where data fusion algorithms are extremely critical. They will bring the disparate types of data generated from various sensors into a manner which can be establishing a certain trend. Okay, like for example, decision about a particular target obtained using a radar system. Is the target potentially a friendly one or is it a hostile one? What is its intent? Which means, is it in a mode where it is likely to attack, or is it in a mode where it is just moving away in a different region of airspace, potentially not contributing towards the intent of hostility. Okay, then what is the typical numerical strength that the target has in terms of multiple target possibilities? All of this requires a radar system information to be processed, analyzed in terms of its various critical parameters of the target. So clearly information fusion from optical or visible light detectors and sensors, which make use of the imaging possibilities in 2 and 3 dimensions, image of the photographic kind and videographic type. Okay, both of them, alongside which works the radio frequency detector types such as radar systems. So the information from each of these sensors needs to be collected, processed, and a unified representation of the specific attribute that is being monitored provided to the pilot. Okay, that's effectively what is data fusion. So data loading involves the abilities that exist in the electronic support systems that are available that will help with providing a very consistent information and sampled data from the real world for the processing purpose. So that is a regulation of the stream of information that is making its way into the processing side of the particular mission computing platform. So weapons aiming, a very dedicated area where, given the fact that the aircraft is traveling at extremely high speeds, the ability of a projectile launched from a weapon in the form of a missile or a possible bomb has indeed the precise chance to reach its intended target, where it can cause extreme devastation without affecting regions nearby. Okay, so the so-called collateral damages have to be kept to a minimum while the weapon systems are deployed. So that is called as the guidance system offered to weapons, and that is in turn controlled by onboard computing systems. So the weapons management involves both the guidance of the weapons as well as a constant update in terms of the nature of weapons that are carried. Is there any way you can relate it to the actual mission or the phase of the particular mission? Okay, so if the mission involves crossing the border and executing a specific attack on hostile regions, you will have to carry a certain type of missiles in the aircraft primarily. Okay, and these weapon systems, as they get deployed or launched from the air platform, certainly would be contributing towards a depletion, which will in turn have a requirement to reconfigure the mission. Okay, so you cannot really take it all the way to its maximum possible case. That's primarily because of the limitations that are imposed in the remaining weapons that are available. So that will mean that depending on how the intensity of the warfare had been, the aircraft needs to come back and reload itself. Okay, so the weapons management involves the overall aspect of managing the onboard weapons carried in the form of close combat weapon systems like the guns and shells that are fired. You have bombs which can be released either with the ability to passively have a guidance scheme on board, or you may also have missile systems such as cruise missiles, air-to-ground, air-to-air missile systems, and so on. Okay, so you have the cryptographic solutions which offer encryption for data communication that takes place across a variety of scenarios between the aircraft to the ground, which has launched the airplane, between aircrafts themselves, from aircraft to satellite systems, and aircrafts to missile systems also. Okay, so this is like a complex communication network that is established for data transport, and all of this data needs to be secure and should be in a manner where it cannot be subjected to any sort of intrusion possibilities. Okay, so that ability is rendered by the use of cryptographic algorithms. Then you have the entire mission being recorded in terms of its greatest level of details regarding the usage of various weapons, the specific phase of a particular mission for which the aircraft was launched, how successful it was, what were the various adversities it had come across. Every one of this is constantly being recorded so that when once the aircraft is on the ground or while it is actually during a mission, telemetry can be used for a live monitoring of the data or a possibly delayed live monitoring of the data. Okay, so considering the lack of line of sight availabilities for access to such data. So the onboard recorders enable such a possibility. Then you have databases that are generated out of the intelligence that is gathered in the form of surveillance reconnaissance. Photo reconnaissance is one important aspect where live digital photography, streaming video in various bands of the EM spectrum, such as optical, infrared, or shortwave, infrared, and all are taken. Radio frequency imaging is also one more possibility, such as synthetic aperture radar. All of this creates a volume of data, and this constitutes what's called as intelligence database. Okay, so that information is in turn processed using massive computational servers that exist at a location on the ground when once the aircraft has come back to its airbase. So you have ECM, electronic countermeasures. Okay, these are in some sense similar to the radar systems that are used specifically with the intent of rendering the hostile radar systems as inoperational. So in that context, you may include parameters such as a jammer. Okay, so a jammer is a scheme that exists in a concept of the electronic warfare such that it typically renders the radar operational abilities dysfunctional. Okay, so you will generate an extremely high strength RF signal, which will completely obliterate any return signals that the radar would be expecting from a target. So the target return signals are completely overwhelmed by the jammer signals. In effect, the radar is considered as having gone blind. Okay, so and you can introduce various smart jamming solutions such as modifying parameters of the target so that the radar system's functionality is totally misled. Okay, so those possibilities come under what is called as electronic countermeasures. So these are also carried on board by aircrafts, and one of the immediate types of aircrafts that comes to mind, and there are a few in fact. So this is the P2I. Okay, so that is the aircraft that is operated as based on the platform, which is a Boeing 707. And this is a US Air Force airplane. And some of the other countries, including India, also operate such an aircraft. Okay. Then you have aircrafts such as the Atlantic, which is from the French manufacturer. And you also have the British Aerospace's Nimrod. So these are some examples of airplanes which are dedicatedly operating as an electronic countermeasures initiative. So in the Indian Air Force, you have a Brazilian aircraft, the Embraer, on top of which you will have the Falcon electronic warfare equipment mounted, that is from Israel. So the Indian Air Force operates equipments from Israel and from Brazil, which have been integrated in order to offer the electronic countermeasures solution. So it primarily is used during active warfare in a manner where it can bring about a non-destructive ability of compromising the war fighting capabilities of the hostile forces. Okay, so that's the idea of carrying this as a mission system aspect on board aircrafts. So coming to the final element, which has to do with display solutions and also abilities to control the various sensors and actuators. In recent times, it has been realized in a unified presentation in the flight deck in the form of touch screen displays. Okay, so you have various types, dedicated displays, which can be used for making sense of the health parameters of the aircraft. Then you have mission displays, which are primarily identified with the specific mission, and this only project information depending on the particular phase of the mission that the aircraft is currently involved in. In addition to that, you have augmented display solutions such as the head-up displays. Effectively, these are transparent devices. You can look through and see what the typical view is outside of the airplane. At the same time, data is projected on the transparent display, so which can also be read. It is very sparse in terms of the nature of the information so that it doesn't clutter the field of view of the pilot. Okay, all the same critical information is projected onto the so-called head-up displays. So you also have visor mounted displays or the so-called helmet mounted displays, and this effectively have an additional capability of also informing the pilot in a given line of sight about critical aspects in the field of view. Okay, so this is like a augmented reality solution. And helmet mounted displays have their visors acting as additional display solutions also. So you have possibilities in addition to this that exist as part of the display scheme. For instance, in the case of the retinal projection, okay, displays and the helmet mounted displays, depending on the cue that has been understood by the display management module, a particular stare or a blink of the eye can give a certain indication, or the turn of the gaze, which means the pupil tracking methods, they are all used to literally slave a particular projectile firing equipment, like a gun, for example. Okay, so depending on various cues that have been ascertained from the movement of the pupils, the stare, the blink of the eye, all of this can in turn mean certain aspects which are used to slave the projectile launching schemes, such as the missile launchers or the gun firing modules, so that depending on what sort of a cue has been gained from the pilot's eye, corresponding realizations in the form of control of the aircraft or the projectiles can be done. So these are integrated in the form of the display and control solutions. All right, so if you look closely at this particular slide, you evidently have the conventional listing out in a manner which is easy to appreciate. Depending on how the broad division of the avionics has been defined for military warfare, okay, towards which aircraft electronics and software systems are deployed extensively. Without too much of a realization from this slide lost whatsoever, you can still retain the overall topology of this layout in a manner where you are now going to interface the various avionics systems. So each one that you see here is an avionics system in its own right. Okay. So what is typically attempted in the combined scheme that uses several sensors, electronics, processing aspects, and display solutions into a single aircraft mission attribute is the way connectivity is defined. Okay, so you can see that here, for example, there are various lines that run vertically and horizontally. Okay, so horizontal lines are used to define the broad classification, and vertical lines are effectively used to identify the subdivisions within each classification. So the same scheme can indeed be applied when it comes to realizing a combination of one or several of these avionics systems, okay, that go into a specific mission that the aircraft has to carry out. So in this context, what we will need to introduce as a new topic of discussion is the so-called architecture of the avionics system. So primarily, it involves establishing the basic connectivity and layout. And this is the fundamental challenge that an avionics system designer has to negotiate when coming up with an avionics system implementation. So the architecture must conform to the overall aircraft mission, and the so-called design aspect has to be very straightforward and less tedious when it comes to problem solving. It should also ensure that the avionics system meets the performance requirements as defined by the mission. So these architectures for avionics systems rely on the primary ability to port data from one to a different avionics system, or from one sensor to a management or computation domain, or data generated from the management units to the various actuators and control signals that they generate. Okay, so this is effectively brought about by the possibilities to bridge all of these various attributes using a backbone communication pathway called as the data bus. Okay, so primarily data buses help with intra-system and inter-system communication. So the optimum architecture can only be selected after a series of exhaustive design trade-offs that primarily would address the various evaluation metrics. So we had seen the utilities. These are the so-called evaluation factors or the evaluation metrics. You will need to certainly come up with a trade-off scenario, because trying to increase the aspect based on a particular relative will try to compromise on another one. Okay, so clearly some trade-offs are involved, which will finally result in a very high grade of outcome for the evaluations that are performed based on such trade-offs. And the architecture is primarily going to enable such possibilities by bringing together the various electronics defined and software defined solutions that go into a particular aircraft, which has to carry out a certain mission. All right, so the system architecture for avionics, okay. How has it evolved over the course of several decades? That is exactly what is shown here. On the extreme left-hand side, you have the initial definitions of the avionics system, similar to what we had seen in the previous slide, okay. So you have, for example, communications, navigations, and identification, CNI. You have sensor systems in the form of radars, management systems for the weapons and the vehicle, or the so-called aircraft or flight management, and display solutions. So each of them is not at all in any manner having a certain bearing on the other. So these remain as independent systems. Okay, with the insertion of technology, which means updates that are being offered by advances in technology, you have a progressive overlap that can be identified among the various avionics systems. So what had remained earlier as hard boundaries without any relevance of one with reference to the other has progressively reached a point where you have now soft boundaries. Okay, so this is called as functional integration. So in every one of this 5 that you see on the extreme left, there is always a possibility to accommodate additional functionality, because they are not during every phase of operation of the particular aircraft or the mission reaching a full utilization, which means that part of what is available within each of these systems can be used for another one. Okay, so that in turn has resulted in a functional integration. So for example, some of the processing abilities or data transport abilities that exist in weapon systems or vehicle management or flight management systems can indeed be made use of during the data loading phase for, say, for example, the CNI or for the radar systems. So that kind of a data loading aspect that is used as a common thread across the various avionics systems is one example of such a sort. Okay, display solutions, again, you can reconfigure them in a manner where a particular pilot would want certain displays to be located at specific points where they find it most advantageous, okay, especially depending on their subjective understanding. So that again is one more element which will mean that displays need to be progressively integrated in a manner where they can receive information about weapons, about the flight management, about the navigation aspects, and the electronic warfare, and the sensor systems such as radars which are carried on board. So with advances in technology, progressively this overlap becomes excessive and also includes additional specialized aspects as part of the avionics system, such as electro-optic schemes, heat-seeking systems, along with imaging systems that go into the overall target detection process. So then you have electronic warfare, data-intensive applications such as displays, the progressive integration that is identified between them and the flight management or the vehicle management system, and the weapons management schemes. So evidently with this insertion of technology, which means advent of new technology, which is constantly deriving a specific benefit for the avionics system because of its incorporation. Okay, has certain positive attributes. Also, there are negative aspects. So let's look at each of these positive ones that are listed along the extreme right hand side. Evidently, the performance of the avionics system has improved because of this functional integration. You have more functionality or performance realization that has been obtained because of the availability of redundant and spare resources of other avionics systems which can be used when there is a peak demand in, say, for example, a CNI or a weapons management scheme. You can indeed borrow the resources from adjacent avionics systems. So functionality has improved evidently. One aspect which is also improved, which is not considered as a positive here, is the so-called cost increase. Okay, because of the less numbers which are being incorporated in aircrafts, considering the nascent level of this technology, which means it has only recently found its way into aircrafts. The supply to demand side has not been favorable for the cost that has been worked out on particular avionics solutions, okay, which have undergone functional integration. So you have substantial number of aircrafts which have got hard boundaries defined within them, and only less numbers going for the soft boundary approach of functional integration, which means cost is evidently going to be severe for the new types of aircrafts. And potentially with this technology gaining ground such that more air forces are going to purchase or deploy them, the cost is likely to come down. You have extreme levels of integration, as I had explained all this while. Reliability has gone up because of the sharing of resources. So if the onboard submodule or an LRU has failed, you can always borrow the avionics systems LRU from an adjacent one. So the supportability or the case for reuse has evidently improved because of, again, the sharing of resources that has been identified. Okay, and the standards that have been set in the avionics system design mean that multiple vendors' products can certainly be used. Okay, so you have software programs which have taken a prominent place, literally reaching a point where they have replaced quite a bit of the hardware solutions. Examples include the smart radar systems, okay, about which I was telling you. So barrage jammers offer a high strength signal, which is hardware intensive. You can also literally mislead the radar system by acquiring the signals that have been operated upon by the radar, aim towards the aircraft, modify certain parameters, and send it back towards the radar system, which can literally mislead the radar, okay, in terms of the nature of the target it is observing. So those are clearly software intensive or algorithm intensive. Such kinds of possibilities as an outcome of the functional integration, again, will mean the software codes and the software deployments are becoming a larger presence in current day avionics systems. Because of the large amount of data generated and processed, you have memory requirements which are also going up. Data throughput, because of the high sampling rates and the massive numbers of sensors which are providing data simultaneously, is also very high. Data handling abilities are proportionately increasing in terms of the bandwidth available for transport of the data, loading of the data, and all that. So the primary data links or the communication pathways or the so-called data bus implementations have become extremely complex in terms of their realization and deployment in avionics systems, because they'll now have to go in for large scale multiplexing, okay, which means that despite the existence of a single data link, it has the possibility to allow multiple types of data to be transported across it. So those kinds of multiplexed data transport configurations are again one more increasing trend that is noticeable. Another thing is the rapid evolution in technology and its direct injection into the progressive changes that are brought out in avionics system design. Okay, so the architecture itself has evolved at a tremendous pace. So what had in earlier times taken 10 or 20 years is in recent times happening over the course of a few months or at the maximum of 1 or 2 years. Okay, after which the technology is considered as outdated. The so-called obsolescence has to do with the speed with which a particular technology is becoming obsolete. Okay, so that is again certainly on an increase. While because of the functional integration, certainly you have all the swap criterion, not the cost criterion, but excluding the cost, all the other three have certainly taken a decreasing trend because of the reduced numbers of implementations that are right now being pursued as an outcome of the functional integration. So you have correspondingly less amount of the electronics that is manifesting itself in the avionics bay. Okay, so which means it occupies less space, does not weigh too much, and the amount of power that is consumed is also less, provided the recent advances in semiconductor technologies also incorporated, such as the gallium nitride and two-dimensional materials. Okay, you have the technology window which is reducing, which means that time taken from the research to its deployment is extremely less these days. Considering that if even a small amount of delay is included in this, you have a new technology which can likely displace this. So there is a massive speed with which the technology has to be inducted into aircraft systems. So the technology window available for eventual location of the evolved avionics architecture is narrowed down quite a bit. Let's take a look at the evolution that has happened in the avionics architecture, which means the nature of the layout of the avionics systems and the connectivity among the various avionics systems for the particular mission that the aircraft is being deployed. Okay, so what sort of a evolution has happened in these two domains? So in the first generation, which is from the 1940s to 50s, you had fundamentally a haphazard nature of the avionics architecture. Literally, there wasn't any to speak of. Okay, so you have the so-called disjoint or independent architecture. So similar to what we had seen on the previous slide, on the extreme left, has 5 separate entities, each of them having no reason to worry about the other. Okay, so that is the disjoint scheme. This was replaced with the centralized architecture. And the example of the aircraft that has such an architecture in place is shown within brackets in each case. So the Russian MiG-21 is for the disjoint case, and the F-111, which interestingly has got a pilot capsule that can detach from the aircraft, and they don't have what is called as an ejector seat. Okay, so the entire cockpit can be detached if the aircraft has met with some calamity. So that's an example of the aircraft, the F-111, which uses the first generation avionics architecture called the centralized architecture. Not very different from that, while at the same time switching to the digital data scheme from the centralized to the federated. You are effectively converting from analog to digital. Okay, so that's when you had the second generation, which is in the 60s to 70s. So the General Dynamics F16 belongs to this particular avionics class. Okay, the architecture of the F16 during the initial phases certainly identified itself with the federated architecture. So the name centralized and federated effectively are the same. Okay, although the distinguishing aspect here is centralized architecture still deals with analog electronics and analog type signals. And we'll be looking at each of this in some detail as we go along. Okay, so while federated deals with the digital scheme of data generation, data formatting, and data processing. After that, you have the distributed architecture, an example of which is the DAIS. It's not an aircraft, it is the technology that is used as part of the DAIS scheme of distributed avionics architecture. Then you have the hierarchical architecture, which is a multi-stage implementation. Again, F-16s are identified with it in their more advanced levels of operation. You also have the European experimental aircraft program. In recent times, you call it as the Typhoon, okay, Eurofighter Typhoon. So that is an example of the EAP during the research and development phase. Then the third generation, also called as the pave pillar architecture, from the 80s to the 90s. You can see that this aircraft has only in the last 5 years gone into deployment in a serious manner. Okay, so the F-22 or the so-called Raptor operated and used by the United States Air Force and effectively developed by Boeing belongs to this class. Okay, then you have the fourth generation, which is effectively not having a furtherance to it. Any generation beyond the fourth generation just constitutes what is called as a open systems architecture. Okay, SOSA is a distinct element beyond the fourth generation. So you have an example of that as the JSF, okay, Joint Strike Fighter, or the F-35. So it belongs to the Lockheed Martin Development Group and is deployed by several NATO countries, including the US Air Force. Okay, so you have the open system architecture, which is a lead up from the fourth generation. You have in effect an ability to achieve massive levels of scalability in the technology by retaining it in a form where you don't anymore identify it with a particular generation, but then it is similar to what you notice with Windows. Okay, Windows beyond the 10, you have just constant updates taking place, and there is no clear definition of a generation beyond that point. So that's the same scheme adapted even here. So you have the generations beyond the fourth generation of avionics architecture classified as the open systems architecture. All right, so in the following sessions for this course, which will be during the next week, considering holidays over the remaining part of this week, starting from Thursday, what you will see is a thorough discussion on each of these architectures. May also remind you that on Thursday, during the time defined in the timetable, the 15 minutes that is available is scheduled for a quiz session, and the complete details of this have already been announced in the MS Teams chat, so you can take a look at it. The material that you can effectively consult for answering questions in the quiz is being uploaded already. Okay, so nothing more than that is by and large required. You can certainly, and you are very welcome to also consult additional reading material which is available online, and I also send you the information related to the textbooks. One among you had asked about it, and the information is already posted in the chat. You can look through those, and effectively the daily course instructions and the slides related to each of the days of this course instructions is already available to you in OneDrive, which you can use for the quiz sessions. By and large, that should be enough. If there are any queries related to what we had discussed in today's session, you can bring them up for clarification.